This is one of my all-time favorite labs. We've got a big, almost 3-liter soda bottle. It's full to a measured mark. And if we zoom in, there's a little hole in the bottle here. What we're going to do is take the cap off. Right now, water's not coming out because the top is closed to the atmosphere, and atmospheric pressure is enough to hold the water in at this hole. We're going to take the cap off and see what happens. All right, so here we go. Not surprisingly, it makes a mess. And what my question is, from how this water's flowing, can we figure out how big that hole is, what its radius is? Let's see how we could go about doing that. I'm doing this lab with equipment I have in my home, so I'll just show you what I have and what we'll need for the classroom. I have extra water because we're going to need to keep the water level at the fill line if it starts to drop below. I have a cup for extra water. I have a way of measuring volume. This is a kitchen measure, and it's in the United States, so it does teaspoons, tablespoons, and ounces. I feel like the best defined of those is ounces, so that's the one I'm going to use. I have a ruler, and I have a whole nother giant bottle of diet soda I have to drink before we can do this lab in class. And I think there's one more after that too. How can we use that to figure out the diameter of this hole? Well, when we draw a picture, the first thing that kind of comes to mind is it looks a lot like a projectile motion problem. If we know the height of the hole above the base and we know how far out it's going, we should be able to calculate a velocity for that water stream. That seems like a good place to go first. It's physics we're pretty comfortable with, and I think that's going to be a major step forward in what we do after that. So let's get a velocity. All right, let's see where it lands. About 13.5 centimeters from the base of the bottle. Our hole, on the other hand, is 14.5 centimeters above the base of the bottle. Let's see if we can calculate a speed from that. So like most projectile problems, I solved the y equation to get a time of flight. I plugged that time into the x equation and ended up with a velocity. What makes this problem different, and the reason we can get back to talking about the pinhole, is we don't have a single projectile. We have a whole fluid that's emptying through that hole. And we know some things about fluids. Particularly in the case of water, it's incompressible. So we can get the volume flow rate by measuring how much water in a certain amount of time ends up in that measuring cup. Once we have the volume flow rate, we can then backtrack and use the equations of fluid, like in the continuity equation, to figure out the size of the hole. So let's get that volume flow rate. Don't forget, the volume flow rate is defined as Q, and it's delta V over delta T. All right, here we go. So we'll just move the kitchen measure in, and we'll time how long it takes to fill it up. Because I used that kitchen measure, I was stuck with the non-standard unit US fluid ounces. So what I did first is I converted that to milliliters. The milliliter is the same as the cubic centimeter. So from that, I was able to get it into cubic meters. Don't forget, when you're doing areas or volumes, you have to multiply one conversion factor for each power of the unit. So not surprisingly, a very small volume in cubic meters. Since water is incompressible, the volume flow rate which is meters cubed per second, has to be area times velocity. In other words, meters squared times meters per second. So coming out with that, we get a radius of 0.00072 meters, or 1.4 millimeters. Just from examining it visually, that seems like a pretty reasonable answer. I'd also like to backtrack and find a prediction using the principles of fluid dynamics for the depth of the hole below the surface of the water. Of course, we can then check that with a ruler. The other thing to keep in mind is we have essentially height of water over here, and we have moving water over here. And when we're trying to compare the behavior of a system in two different locations, conservation of energy has often been pretty useful. We can use the Bernoulli equation here as a form of conservation of energy. If we think about it, over here water's got potential energy, over here it's got kinetic energy. We have to pick two locations to compare, and I want to pick right here where we know the velocity, and I want to pick right here. The goal of this is we're going to try to figure out how high the water level was above the hole, and of course that's something that we can check. So here's our setup for the Bernoulli equation. We're essentially comparing this location at the top of the water where it's roughly still to where the water's coming out where it's moving. Both of these are exposed to the atmosphere, so the pressure in each case is atmospheric pressure. So there's our Bernoulli equation. We can see the pressure terms cancel because they're both atmospheric, and we're essentially left with the term that roughly corresponds to potential energy being equal to the one that roughly corresponds to kinetic energy. We solve for height and plug in, and we end up with 3.1 centimeters. How does that compare to reality? In reality, it was about 11.5 centimeters. What could have us off by such a huge amount? Well, to get the speed we saw, we only needed a fourth of this height. What that means is that it's leaving slower than it should. And I think the culprit has to come down to the pinhole itself. I drilled this by knocking a hole with a nail into the bottle, and you can see it's kind of ragged and jagged and things. Water molecules tend to hold on to each other. They have a lot of surface tension, and I think there's probably some surface tension that's preventing water from coming out as fast as it should. Now, of course, if you make a claim that the hole's too small and that's what's stopping the water from coming out effectively, you have to check that. I did a literature search, and most other people doing this experiment, which is called the Toricelli experiment, used a much bigger drill bit to make a hole. I just used a nail to poke a hole. So I'm going to use a 5/32 inch drill bit. We're going to see if a bigger hole makes any difference. All right, we got our bigger hole. Let's try again. I've had a bit of a change of venue from my dining room table because I think this is going to make a much bigger mess now. But we'll know right away. The first stream of water only went to 13.5 centimeters. If this goes farther, we'll know that we're on the right track. So, trying to prove Torricelli's theorem, step 2. And I saw 22.5 centimeters for that one. Let's see if that gets us any more reasonable results. Okay, so we redo the calculation for speed. Of course, the time of flight ends up being the same since the height of the hole is the same. But because of the greater horizontal distance, we have a much larger horizontal velocity. We'll do our Bernoulli equation. We'll take location 1 to be the top of the water, which is still. Location 2 to be just outside the hole. That essentially leads us with potential energy equals kinetic energy, and we solve, and we get almost 9 centimeters. Let's see what that looks like on the bottle. So we could see the actual height is a little more than 11.5 centimeters. So we're much closer to what the actual height is, but we still have some error in here. At this point, what I'd like to do is have this bottle be used by some groups in the classroom. We'll drill some bigger holes on other bottles to see if that makes a difference, since that certainly helped here. And we'll also, in class, check various heights above the hole so we can explore Torricelli's law in a little more detail. When you have an experiment that gives you results with quite a bit of error, in an actual scientific lab, you would redo the experiment until you were confident in the results. We're not going to do that for every lab in this class, but I'm glad we were able to get a more reasonable answer than we had at first. So one thing that should be obvious as this starts to drain and the height of the water level drops is that water's speed leaving the hole is different as time passes. We're going to look for patterns in lab. We're going to have you check several different initial heights above the hole, and we'll see if we can find any patterns that we can figure out the relationship. I have a helper, if you can't tell.